So last time defined a complex number in the form alpha plus I beta, and alpha and beta are real numbers, and I is square root minus 1 with I squared equals minus 1. And we saw some properties. So for example, we saw that, if we define Z as alpha plus I beta, then Z bar, called conjugate of that complex number, is defined as alpha minus I beta, and we have Z times Z bar equals a norm Z the whole squared, which is alpha squared plus beta squared. All right, now let's look at some more properties. So for example, Euler formula. Euler formula is a very basic and important formula in complex analysis and in the set of complex numbers. Euler formula e to power, maybe I can call this one number 1, e to power I theta is equal to cos theta plus I sine theta. So e to power I theta still denotes an exponential function, but our variable here is a complex number. So you're familiar with the function e to the x. So here, instead of e to the x, we have e to the ix. You can say e to the ix, but normally we write e to the I theta. It doesn't matter. You can say e to the ix equals cos x plus I sine x. But here I called my variable theta. So this is called Euler formula. Let's look at the proof for this first. Proof. We will use the Taylor series for an exponential function. Taylor series for exponential function. So we know that e to power I theta can be written as 1 plus I theta plus I theta the whole squared over 2, I theta the whole cube over 3 factorial, I theta to power 4 over 4 factorial, plus so on. Here we use the fact that e to the x can be written as 1 plus x squared over 2 factorial, x cubed over 3 factorial, plus other terms. So this is called Taylor series for exponential function. And we use the same Taylor series, we replace x with I theta here. Now, if we simplify the right-hand side of the equation above, we can write it as 1 plus I theta plus, now this one I theta the whole squared, we can write I squared theta squared, but I squared is minus 1. So we can write it as minus theta squared over 2 factorial plus this one I to power 3 can be written as I squared times I squared is minus 1 times I will be minus I. And then I to power 4 here. I to power 4 means I squared, the whole squared. I squared is -1. -1 squared will be 1. So then this will be 1 times theta to power 4 over 4 factorial and plus the remaining terms. Now, if I rearrange the terms here, I can write it as 1 minus theta squared over 2 factorial plus theta to power 4 over 4 factorial minus theta to power 6 over 6 factorial plus I times, so for the remaining terms, let me take the common factor I out, and what will be left? So these terms, I regroup them together, these ones. And now I want to regroup these terms together, plus the next ones. So from the first one, theta will be left. And then minus theta to power 3 over 3 factorial plus theta to power 5 over 5 factorial. And this is the Taylor expansion of, if you look at these two Taylor series, this one is a Taylor series of cos theta. And this one is Taylor series of sine theta. And we can write this one as cos theta plus I sine theta. Cos theta plus I sine theta. So this whole series is cos theta, and this whole series is sine theta. So we started with e to I theta, and we wrote it as cos theta plus I sine theta. All right, let's look at more properties. Now, what will be the magnitude of e to power I theta? So magnitude of e to power I theta, if you remember, to find magnitude of a complex number, if I multiply z with z bar, I'll get magnitude z squared. So here, z is e to power I theta. So z times z bar will be e to power I theta times e to power minus I theta. Remember, to find conjugate of a complex number, we just need to simply replace I with minus I. Then we get e to power I theta times e to power minus I theta, and this is e to power I theta minus I theta, and that's e to power 0, which is 1. So that means norm z squared is 1, and because norm z is always a positive number, remember, we use Pythagoras to find norm z, and it's always a positive number, norm z. So if norm z squared is 1, then norm z or magnitude of z would be 1. So this is a complex number with magnitude 1, e to power I theta. So what does that mean? That means this number can be used to solve the equations of the form z to power n equals 1. So since z equals e to power I theta as magnitude 1, we can conclude that this is a root of unity and we can use it to find the solutions of the equation z to power n, or let's say x to power n equals 1. Well, x to power n equals 1. This looks like a very simple equation. And maybe in high school, if someone asks you what is the solution of x to power n equals 1, you would say, well, if n is odd, like x cubed equals 1, then x equals 1. And if n is even, for example, x squared equals 1 or x to power 4 equals 1, then you would say x is equal to plus or minus 1. Well, this solution that we just mentioned is the solution in the set of real numbers. But if we want to consider all solutions, whether real or complex, then the answer is not as simple as x equals 1 or x equals plus minus 1. See, when we have x to power n equals 1, if I take magnitude from both sides, I'll get magnitude x to power n equals 1. And that means magnitude x, because magnitude x is always positive, that means magnitude x equals 1. So the solution of this type of equation, if we have a complex valued solution, then the magnitude of that solution has to be 1. And we just verified that the magnitude of this number here is 1. So that's why we are saying that since we already found out that the magnitude of this complex number is 1, we can use this type of number, this type of complex number to find the solutions of this equation. Now, how many solutions do you think this equation has? X to power n equals 1. But again, in the set of real numbers, either 1 or 2 solutions only. But in the set of complex number, if you want to consider all solutions, whether complex or real, x to power n equals 1 will have n solutions. In general, it can be proved that if you have a polynomial of degree n, when you consider all solutions, whether real or complex, any polynomial of degree n will have exactly n solutions. Any polynomial of degree n has exactly n solutions as long as you consider all solutions, whether real or complex. So for example, any quadratic equation has 2 solutions as long as you accept complex valued solutions as well. So x to power n equals 1 must have n solutions, and any solution must be of this form. But we want to exactly find all n solutions. So we know that it's of this form, but there are many values of this form. For example, is it e to power, because theta could take any value. So for example, is it e to power I times pi, or is it e to power I times 2 pi? What is that going to be? So now we want to solve. Now we will find all solutions of x to power n equals 1. So note that by a theorem, we know that any polynomial of degree n has exactly n roots in the set of complex numbers. So we know that we are looking for n solutions here. What will be the n solution? So let's substitute x with e to power I theta, and we want to find theta here. So we know that x to power n is 1. So that means e to power I theta, the whole to power n is 1. And that means e to power I n theta equals 1. I wrote x as e to power I theta, x to power n is 1. That means e to power I theta, the whole to power n equals 1. And e to power I theta, the whole to power n can be written as e to power I n theta. Now if we use the Euler formula, we can write e to power I n theta as cos n theta plus I sine n theta. This has to be equal to 1. And that means cos n theta has to be 1. And sine n theta has to be 0. Now cos n theta equals 1. You know from pre-calculus that if cos t, let's say, equals 1, that means t is equal to 2 pi k. From pre-calculus, we can say that n theta is equal to 2 pi k. And once n theta is equal to 2 pi k, sine n theta will be automatically 0 as well, because sine 2 pi k is 0. So we just need to guarantee or make sure that cos n theta is 1, because then that gives n theta is equal to 2 pi k, and the unit circle C2 pi k will be this point here. And if you're on this point on the unit circle, cos is 1 and sine will be automatically 0. So once I make sure that this happens, this will also automatically happen. So n theta will be equal to 2 pi k, and that means theta is equal to 2 pi k over n. And k is an integer here. K is an integer. So basically we can say that the distinct, but remember we were looking for n solutions. But here k is any integer, so you may say, okay, if k is integer, that means there are infinitely many choices for k. Does that mean we have infinitely many solutions for our equation? Well, there are infinitely many solutions for k, but there are still n distinct solutions. The rest of the solutions will be repetition of the previous solutions. So the distinct solutions of x to power n equals 1 are z equals e to power 2 pi I over n. This is corresponding with k equals 1. With k equals 1. And if k is equal to 2, we will have z equals 4 pi I over n. With k equals 2. And z equals e to power 6 pi I over n with k equals 3. All the way to z equals, if I replace k with n, here, replace k with n, then I'll have 2 pi n over n, which is 2 pi. So e to power 2 pi I, which is 1. See, so far I got n solutions. This is my theta, and my solution was e to power I theta. My solution was e to power I theta, and I have the value of theta here. So you just need to substitute and use different values for k. If k is 1, theta will be 2 pi over n. Therefore, the solution will be e to power I theta, and theta is 2 pi over n, so it will be 2 pi I over n. If k is equal to 2, solution will be e to power 4 pi over n. If n is equal, k equals 3, the solution will be e to power 6 pi over n. And all the way to if k is equal to n, the solution will be e to power 2 pi n over n, I, which is e to power 2 pi I. And e to power 2 pi I means cos 2 pi plus I sine 2 pi, and that's just 1. And of course, 1 is a solution for x to power n equals 1. So we were expecting to get 1 as one of the solutions. What about the rest of the solutions? So note that the rest of the solutions are the repetition of solutions above. So we already got n solutions, and the rest of the solutions are the repetition of solutions above. All right, let's see why these solutions, the rest of the solutions are the repetition of the previous solutions. So here are the solutions where k equals 1 all the way to n. Now, let's say if k is equal to n plus 1, what do we get? Because if k is equal to n plus 1, then z will be equal to e to power 2 pi n plus 1 over n. And this is same as e to power 2 pi I 1 plus 1 over n. That's e to power 2 pi I plus 2 pi I over n. And this one we can write e to power 2 pi I times e to power 2 pi I over n. E to power 2 pi I is 1. So this is same as e to power 2 pi I over n. So z is equal to e to power 2 pi I times e to power 2 pi I over n, and e to power 2 pi I, we solve it for it's 1 because cos 2 pi plus I sine 2 pi, and this is basically 1. Therefore, the solution corresponding to k equals n plus 1 is same as the solution corresponding to k equals 1. E to power 2 pi I over n was the solution corresponding to k equals 1. This is same as solution corresponding to k equals 1. Similarly, the solution with k equals n plus 2 is same as the solution corresponding to k equals 2, right? And so on. With n, k equals n plus 3 is same as the solution with k equals 3, n equals 4, n plus 4 is same as solution with k equals 4. all the way to k equals 2n is same as solution with k equals n. K equals 2n plus 1, again, will be same as solution with k equals n plus 1, which was same as solution k equals 1, and so on. So here, basically, we have period n, and after n, everything repeats itself after n units. All right, so let's look at an example. Find the solutions of x to power 3 equals 1. Find all solutions of x to power 3 equals 1. Well, again, in high school, you would say the solution of x to power 3 equals 1 is x equals 1. But here we know that when we extend our numbers to complex numbers, then every equation of degree n has exactly n solutions. So x to power 3 equals 1 must have exactly 3 solutions. So here n equals 3. So what will be the solutions? We just derived our n solutions or n roots for x to power n equals 1. Z equals e to power 2 pi I over n, 4 pi I over n, all the way to 2 pi I times n over n, which is 1. These are the n solutions for my equation. So here we will have the solutions according to calculation above. Our 3 solutions for x to power 3 equals 1 are x equals e to power 2 pi I over 3, x equals e to power 2 times 2 pi I over 3, and x equals e to power 3 times 2 pi I over 3. Now, if you want to simplify these 3, namely x equals, so this one e to power 2 pi I over 3, we know that e to power I theta is cos theta plus I sine theta. So this one is cos 2 pi over 3 plus I sine 2 pi over 3, which is minus 1/2 plus I root 3 over 2. And then the other one, x equals this guy here, e to power 4 pi I over 3. E to power 4 pi I over 3, we can write it as cos 4 pi over 3 plus I sine 4 pi over 3. And this one we can write it as minus 1/2 minus I root 3 over 2. And then the other solution would be e to power 3 times 2 pi I over 3. And this is same as e to power 2 pi I. 3 times 2 pi I over 3 same as 2 pi I. And e to power 2 pi I means cos 2 pi plus I sine 2 pi. And this is 1. So our 3 solutions are x equals, if I want to list them one more time, minus 1 over 2 plus I root 3 over 2, minus 1 over 2 minus I root 3 over 2, and 1. But obviously we expected 1 to be one of the solutions because 1 to power 3 is of course 1. But You can also verify that, for example, this number -1/2 plus I√3/2. If you raise it to power 3, you know how to raise a number to power 3, right? Like, for example, a plus b to power 3, the whole to power 3 is a cubed plus b cubed plus 3a squared b plus 3ab squared. So use that identity and use the fact that I to power 2 is -1. And do the calculation, you will see that x to power 3, if x is -1/2 plus I√3/2 will be 1. Similarly, you can check that if x is -1/2 minus I√3/2, again, x to power 3 will be 1. And for 1 itself, it's obvious that 1 to power 3 is 1. All right, so these are the solutions for x to power 3 equals 1. As an exercise, you can find the solutions of x to power 4 equals 1 or x to power 5 equals 1. And in general, we just showed that x to power n equals 1 has exactly n solutions, and we found those n solutions. Now let's go back to our topic of differential equations. So back to ODE, or second order ODEs basically. So consider y double prime plus by prime plus cy equals 0 with b squared minus 4c less than 0. So let's assume that this is our differential equation. So here we used y equals e to power rx, if you remember. So we saw if we use y equals e to power rx, is a solution if r is the root of the characteristic equation r to power 2 plus br plus c equals 0. So this is what we have seen before, that if you replace y with e to power rx and substitute back, you will see that as long as this equation is satisfied, then this will be a solution for our differential equation. And this equation is called characteristic equation for the differential equation. We saw that to find the characteristic equation, we have to simply use the same coefficients, but instead of order of derivatives, we need powers here. So instead of second derivative, we'll have power 2 and then power 1 and then constant here. So now here b squared minus 4c is less than 0. So this equation, this characteristic equation, will have two complex roots. So since b squared minus 4c is less than 0, the equation above has two complex roots, namely r1 equals minus b plus root b squared minus 4c divided by 2, and r2 equals minus b minus root b squared minus 4c divided by 2. Now, we can write this one as, let's say, alpha plus I beta. And then this one will be alpha minus I beta. We can write them of this form. And what is alpha and beta here? Where alpha, we can write it as minus b over 2, and beta will be root 4c minus b squared divided by 2. Because we can write this one as minus b over 2. See, I can write this one as minus b over 2 plus, instead of root b squared minus 4c, because b squared minus 4c, according to my assumption, is negative. So I can write it as root 4c minus b squared times root minus 1. See, root 4c minus b squared times root minus 1 is same as root b squared minus 4c. And then divided by 2 as well. So basically, I'm saying that this is my alpha and this is my beta. And we can write R1 as alpha plus I beta. Root minus 1 is I, right? So we can write it as alpha plus I beta. Similarly, we can write R2 as alpha minus I beta. So this is how we can write R1 and R2. So what will be the solutions? So the solutions will be y equals e to power alpha plus I beta x and e to power alpha minus I beta x. And this one we can write it as, first one we can write it as e to power alpha x plus I beta x. And this one I can write it as cos, I can write it as e to power alpha x times e to power I beta x, e to power alpha x, e to power I beta x, I can write it as cos beta x plus I sine beta x. And the other solution, e to power alpha x minus I beta x. I can write it as e to power alpha x times e to power minus I beta x. And I can write this one as e to power alpha x times cos beta x minus I sine beta x. So here we have these two solutions. But these are the solutions and they are linearly independent as well. But the problem is that they are not real valued. Here, because our differential equation, they're all real valued, the constants are real numbers. So we prefer our solutions to be real valued as well. Because so far we only learned about real analysis, how to differentiate, for example, real valued functions. We don't want to go into complex functions or complex analysis. So we want to write our solutions. We still want our solutions to be linearly independent. We also want them to be real valued. So how can we do that? So let's say if I call this one y1 and this one y2, call them y1 and y2. Well, we know that if y1 and y2 are solutions, then any linear combination of y1 and y2 will be still a solution for our differential equation. So here, if I, for example, add y1 and y2, I will still have a solution. And if I add y1 and y2, I will get a real valued function. So now, to find two linearly independent real valued solutions. Let's consider, let's say, for example, W1 as, or let's say, G, maybe I can say G1 as Y1 plus Y2 over 2, and G2 as Y1 minus Y2. What about if I consider Y1 minus Y2? Y1 minus Y2, this guy minus this guy. So these will cancel out, and I'll get 2I sine beta x times e to the power alpha x. Not real valued, but if I divide it by 2I, it will become real valued. See, let me explain one more time. When I add Y1 and Y2, see, if I add these two functions, this complex the complex parts cancel out, and I'll be left with e to the power alpha x cos beta x plus e to the power alpha x cos beta x, which is 2 e to the power alpha x cos beta x divided by 2 will be e to the power alpha x cos beta x. So you can see why I divided by 2 here. So this addition appeared because I wanted to get rid of the complex part. I wanted the complex parts to cancel out each other. And when I added them, I got extra factor of 2. If I divide by 2, I will get rid of that factor as well. And I am allowed to divide by 2 because we know that any linear combination of y1 and y2 is a solution. Here, basically, when you say y1 plus y2, the whole divided by 2, it's basically same as 1/2 times y1 plus 1/2 times y2. So this is a linear combination of y1 and y2, and therefore this is a solution for my equation. Similarly, y1 minus y2, y1 minus y2, if I subtract this with this, I'll get 2I, because the real parts this time they cancel out each other, and I'll be left with 2I e to the power alpha x sine beta x divided by 2I, and that's e to the power alpha x sine beta x. So here I get 2 real valued functions. That's the first thing that I was looking for. And note that G1 and G2 are solutions for our ODE, since G1 and G2 are linear combinations of y1 and y2. So that's the first thing, that because these are linear combinations of y1 and y2, they are solutions for our ODE. And I just need to now verify that G1 and G2 are linearly independent, because I was looking for 2 solutions. I was looking forward for them to be a real valued, and I also want them to be linearly independent. So if I can verify that they're linearly independent, then I'll get all I needed. Moreover, G1 and G2 are linearly independent, since I can use Wronskian here. Wronskian of G1 and G2 is determinant of G1, G2, G1 prime, G2 prime. And then this will be same as determinant. G1 here is e to power alpha x cos beta x. And then e to power alpha x sine beta x. And then alpha e to power. So I also need derivative of G1. How can I find derivative of G1? Derivative of G1, we can use the product rule. So I will have alpha e to power alpha x cos beta x minus beta e to power alpha x sine beta x. Let's put a comma to distinguish between the different terms. And derivative of G2 is alpha e to power alpha x sine beta x plus beta e to power alpha x cos beta x. Determinant of this. And then this will be this guy times this guy minus this guy times this guy. So it will be e to power alpha x cos beta x times alpha e to power alpha x sine beta x plus beta e to power alpha x cos beta x. So this guy times this guy minus this guy times this guy. So minus e to power alpha x sine beta x times alpha e to power alpha x cos beta x minus beta e to power alpha x sine beta x. Now, if we simplify this, I'll get alpha e to power 2 alpha x cos beta x sine beta x minus, again, alpha e to power 2 alpha x cos beta x sine beta x. So this term here will cancel out with this term here. And then I'll be left with, now this term times second one will be beta e to power 2 alpha x cos squared beta x plus beta e to power 2 alpha x sine squared beta x. And this one I can write it as beta e to power 2 alpha x times bracket cos squared beta x plus sine squared beta x. Cos squared plus sine squared is always 1. And then this is beta e to power 2 alpha x, which is not equal to 0 for every x. Since beta is not equal to 0, and e to power 2 alpha x is also not equal to 0 for every x. So Wronskian is not 0 for every x. Please remember that even if Wronskian is not 0 even for one value of x, that would be enough to conclude that the functions are linearly independent. But here Wronskian is not 0 for every x. So we can conclude that the functions are linearly independent. So G1 and G2 are linearly independent. So by the way, when I said beta is not 0 here, because the reason was that when we look at the expression for beta, beta is this. Well, we were assuming that b squared minus 4c is negative. So negative of that number, which is 4c minus b squared, will be positive. So this number, according to my assumption, is positive. Root of it will be also positive. Divided by 2 will be still positive. Therefore, beta is non-zero. So G1 and G2 are linearly independent. So the summary is, so we showed that two real valued linearly independent solutions of y double prime plus by prime plus cy equals 0 with b squared minus 4c less than 0 are y1 equals e to power alpha x cos beta x and y2 equals e to power alpha x sine beta x, where alpha is minus b over 2 and beta is root 4c minus b squared divided by 2. In other words, alpha, or you can write, or you can say that, or equivalently, we can say that alpha plus minus I beta are the roots of the characteristic equation. So if you don't want to memorize these formulas for alpha and beta, you can simply say that alpha plus and minus I beta are the roots of the characteristic equation of our differential equation. So let's look at an example.